Okay. HIP also defines a number of vector types with n is equal to 1, 2, 3, and 4 elements. Now, this is different from OpenCL. So we're just beginning a new section. Now we're talking about vectors in HIP. So HIP, defines a number of vector types with n is equal to 1, 2, 3, and 4 elements. So in OpenCL, you have 1, 2, 3, 4, then you have 8 and 16 element vectors. So OpenCL is more capable in that sense than CUDA and HIP when it comes to vectors. So vectors can unlock performance within a HIP application because memory is loaded into cache using cache lines that are typically 16 to 32 floats wide. So furthermore, CPUs and some GPUs have SIMD units that can process in one instruction vectors of floats. So here are the vector types used within HIP, and this is accessible both in host and kernel code. So these are the different types, and you've got the size of each type there. So in HIP and in CUDA, access to the individual components of the vector from both host and kernel is through a structure. So you can access up to X, Y, Z, W, and those are the individual components of the vector. So in this program, vector types is code to muck around with vectors. So we've got the size of the different vector types. In this case, it's a vector of length 1, but we've got code, for example, how to allocate a float 4 vector. So that's a vector of 4 floats. Then we're accessing individual elements of that vector. Another way to allocate a vector, and then again another way to allocate a vector using the make float 4 function. So that is just mucking around with vectors, and that works fine on NVIDIA architectures. So that's how we work with vectors in a kernel as well. Now, there's something to note with using vectors is that when you're using AMD architectures, you can actually treat vectors as individual entities when it comes to math operations. So for example, in AMD architectures, I could do temp2 multiplied by temp3, and then that would multiply the elements element-wise. In NVIDIA, with an NVIDIA CUDA backend, this capability is not there. So you need to individually go temp2.x times temp2 temp3.x is equal to temp something.x. So you need to do operations on individual elements in CUDA. So it doesn't have support for bulk vector math like you do in OpenCL and AMD. So that's just something to be wary of, and in fact it tripped me up because I developed this module on a AMD backend, and I thought that vector math was native, but it isn't on a CUDA backend. So just need to be wary of that. Yeah, so when using vectors, there is potential to get speed up on either architecture, on AMD or NVIDIA. And the reason is because on an AMD architecture, the GPU has support for SIMD operations, as far as I understand. And on NVIDIA architectures, you can still get a performance benefit from vectors because using vectors is contiguous memory, and that's kind of like a signal to the compiler to optimize memory transfers. So using vectors can be good for both AMD and NVIDIA backends. Complex numbers are not implemented natively in HIP, but you can store the real and imaginary components in a float2 or double2 vector type. But one must perform manually the complex number math operations on the individual components. So you just need to be aware of that. So if you're doing Fourier transformations, for example, your real and imaginary components can be stored in a float2 or double2 vector, but you just have to do the operations individually on the real and imaginary components. Okay, so in this program, matmult shared a vector. We extend the shared memory solution to work with A and shared A as allocations of vectors of type 4. So type float 4. So if we go down to here, so this is, I'll just close all these other ones down. Okay, so this is the vectorized version now of a shared memory implementation of matrix multiplication. So what we're doing is we are dynamically allocating our memory as before, but then we're interpreting that shared memory as float 4 vectors. So that's what we're doing. Now we need to pass in. Now if we're doing it in vector form, that means the axis N1A gets reduced to N1AV. So N1AV is the number of vectors along N1A. So that's what N1AV is. We can still get our coordinates I0 and I1. It's just that we're going across this dimension now in jumps of 4. So when we're looping over, when we're trying to fill our vector array, we can loop over A, and with start and end, we're using N1AV instead of N1A. So N1A, we grab the number of sections to copy. So that's L1 is the number of sections to copy. And the number of sections to copy is N1AV. So every thread in the block now copies a set of vectors instead of a set of elements. So they're copying that now into shared A because we're interpreting shared A as vector, as memory of vectors now. So we do that, we bring in the shared memory, and then we have our synchronization point. And we have these temporary variables now of type float 4. So float vec type is defined up here as float 4. Okay, so that's our vector type. Okay. So we can interpret A as being float vector type. So we can interpret, we have allocated and we have brought in matrix A as of type float 4, but we have brought in B as float type. And that is because we need to go down a column. Now, if we had interpreted B as vectors, they would be along this way, and it would be more difficult to get at these columns. So I've left B as normal float type. But what we can do when we're doing the dot product is we can define a scratch vector, and then fill elements of that scratch vector. And then when it comes to doing the dot product, we then do the bulk vector math operation. Now, when we get to the end, we're walking across this row and down this column. When we get to the end, we of course need to accumulate the values that inside the vector, and then that becomes the value which we're setting for C. So that's how we're doing vector math. So this code here, that is a vector multiplication. And as we discovered during the compilation step, that doesn't work on an NVIDIA backend. So what I'll do just for this exercise, or just for this, is I will switch back to my AMD backend. So I'll go HIP course, change directory to course material, and then I will go to L6 memory management, and then I'm going to unset HIP platform. That is going to get me back to using my AMD GPU, my AMD integrated GPU. So I now compile all that code again using the AMD integrated GPU. And on Photonics, of course, you will have this this ability to do vector operations, vector math. It's just with the CUDA backend, we don't have that. So see how we don't have a compiler error now. So now I can run. Now we don't have that compiler error. Now I can run this code. Matmult shared a vector, and I'll just, oops. There we go. And we were able to get the same result as, well, pretty much the same result as before. Okay, so what I've got to do is I've got to have some some AMD and CUDA specific macros. And there are those macros. Those macros do exist. I just have to go into the kernel optimization section, and I will grab this. And so when you're running with a CUDA backend, then this macro HIP platform NVIDIA will be defined. So that macro will be defined, and that macro will be defined so that then you can have NVIDIA specific code inside this region, and then just normal code outside that region. So that's how you can maintain a measure of portability between AMD and NVIDIA backends. Okay, so we've finished the section on using vectors. And if you are around for the advanced course, I'm actually going to see what kind of a difference the performance of using vectorized operations makes on the runtime of a kernel. But that is not for the beginner course, that is for the advanced course, which is going to happen in early October. Okay, so we have run the vectors. We've shown that it produces roughly the same result as before. The next section is to talk about atomics, and this is the final section for this module. So at the time of writing, support for atomic functions in HIP. So an atomic function is one that is only run by one thread. One thread in the system. at a time. So a kernel launches, and then an atomic operation is limited to running by one thread. And so all the other threads have to wait in order to run that atomic operation. So that's what an atomic operation does. So in CUDA, there is support for functions like atomic add that provide atomic operations with device level synchronization. So that means the operation is atomic for all threads executed on the device. The function's atomic add system can provide system level synchronization. So the host can atomically increment as well. And atomic add block can perform an atomic add that is synchronized over all threads in a block. Okay, so in the program atomics, what we're going to do is we're going to allocate a single integer that is going to be incremented by a kernel. So a single integer is going to be incremented by a kernel, and we make our grid of size 256 by 256, and our block size is 64. Okay, so there's going to be 4 blocks. So each block, sorry, there's going to be 256 divided by 8, or 64. Yeah, 64. Oops, sorry. Yep, so there's going to be 256 divided by 8 blocks along each dimension of the grid. And so there's going to be 64K or 65,536 threads over that grid of size 256 by 256. And each of those threads are going to try and increment this counter. So we've got our allocation of memory. We've got our allocation of memory, and our memory that we're allocating is just a single integer. So that's going to be in our global memory space, this single integer. And we are bringing in that single integer. We're bringing in that single integer for use by this atomic add function. And that will make sure that that single integer is incremented atomically. So if the number that results out of that is not 65536, then it hasn't been done atomically. So if we then make that and run that, we see that the counter has indeed been run 65536 times out of 65536. So that is a brief introduction to atomic operations within HIP. That is using, so that is for whenever you need atomic operations. Okay, so that is the end of this, the teaching section of this module. Now we do have an exercise that is associated with this section. And so what we're doing is we are doing rectangular copies. That's interesting. We're doing rectangular copies for our element-wise matrix multiplication. So for the exercise, we've got our usual Hadamard matrix multiplication, which is just element-wise. And using rectangular copies is an important skill to master, particularly when you are decomposing your problem into sections that are to be handled by different compute devices. So in this exercise, we're going to enable the element-wise matrix multiplication code to use a rectangular copy to copy the memory allocation FD back to the host FH. So the code itself is defined in mat element-wise. So we've got the code here. So that's the code there, and it works fine. So it just uses hip memcopy to copy that memory from FD to FH. So as it stands, it produces the right answers, namely 0 residual. But your task is to your task is to use hip mem copy 3D in order to perform that memory copy using a rectangular copy. Okay, so using hip mem copy 3D, can you change this hip mem copy to use hip mem copy 3D? So that's the task. And you can use the example code from matmult pitch mem as template code, so you can copy paste. You can copy paste that into mat element wise and begin your modifications. As a bonus task, you can experiment with this 3D copy. So can you change it so that it only copies back a rectangular region inside FD, leaving a one cell border wide all the way around? So can you copy only this interior region here? Can you copy that back? So you can, of course, look at the answer, and the answer has the hipmem copy 3D code in it. But yes, so this exercise is designed to give you experience working with hipmem copy 3D. Okay, so let's finish that. And we are done.